All right, let's get started. Sorry for the delays there. I was just trying to do some things to try to get rid of some of the garbage that's on the screen here, but it looks like I'm going to be limited unless I try to be a little more clever. It's one of these, so I'll try to work on this throughout, but these, for those of you who ever end up making decisions about IT infrastructure, these Zoom rooms are sort of designed for conference rooms, not classrooms. And so there's a lot of things that, like, in order for me to use an audio device that doesn't sound like crap remotely, I have to, not use these wastes of space in the ceiling, which means they're always picking up audio that Zoom rooms is always going to then portray them saying, well, by the way, we hear audio in the room, don't you want to unmute? So we're stuck with this toast here with the unmute. So there's a couple of things I'm experimenting with to get rid of that, but it's kind of a known limitation with this thing. And so, so this is just something we'll work through, and I'll see if I can come up with more clever ways to do this as we go. But yeah, anyways, that's the reason for some of the delay this morning. All right, so where were we last time? Well, we left off kind of defining the basic problem here. And so I'll call this lecture 1B. And this is going to be our intro to evolutionary algorithms and in the GA. So we'll see that in a second. So we have been, and again, for those of you who are online, I've got the chat up over here. So if any questions come up, feel free to put in the chat. If you want to unmute, I can also take those questions. Any question asked online, I'll repeat for those in class to hear it and vice versa. Okay, so we were kind of focusing on the problem, which I'll say that comes from engineering design optimization. Or EDO. And the basic idea here is we are focused on the mathematical problem of minimizing some function that for now I'll just call f of a vector x, such that this vector x comes from some subset x, which could be discrete or continuous. And in optimization, when we say minimize, this could also be maximize. So if we wanted to maximize a function, that is equivalent to just saying minimize minus f. So this generalizes to maximization problems as well. So I'll give some examples of these sorts of problems in just a second, but abstractly, we are saying that f, where the function f is potentially, and we'll say costly to compute, has many local optima, and is a function of many variables. And so we're saying here that formally this vector x is maybe say in Rn, where n is very large. So it's a vector with a lot of elements here. And so the costly to compute might mean that we also have a computation budget that we're dealing with. So it might be that if we use a computer tool to help us with this problem, we might have a limited amount of time that, so we only have so many hours on the supercomputer, or so on. So we have some budget that, we can't just let this thing churn forever. And then when I say local optima, I'm also including other complications like singularities and saddle points. So a lot of ugly things that would make it difficult to optimize or to use, so what basically makes it very difficult for to do in an automated way. So a lot of times when we think about optimization problems, if we don't have a good mathematical way to go, we might just think of doing a brute force search. In other words, try every single possibility for X and then see what all the different F's are and just sort them. But these sort of things are going to make it impossible to do a simple brute force search. Now, so we say, well, yeah, question.
Does X have to occupy all of Rn? Could it have like certain constraints on it?
Well, no, I guess it's in Rn, but it's actually in a subset. So I could say here that this X that I've mentioned up top here, this is a subset, possibly strict, but not necessarily. So it comes from a subset of Rn. So constraints are involved in here as well. So it is a constrained optimization problem generally. All right, so we have to say, well, what is this F? Well, this F may not even be, this F might only exist in the abstract. It may not be something that we could actually write down or even hope to write down. So what do I mean by that? So in engineering design optimization, so F could be, so I'm gonna flip to the next page here. So I could say F examples of F, the thing that we like to optimize. So it could be, for example, a high fidelity simulation model. Of some physical process. So, you might say we're working on a jet engine, so we build a simulation model. That jet engine has a bunch of different parameters in it, some fuel oxygen mixture that we can set as design engineers, maybe has certain sizes, certain parts, different fuel types. There's all these different parameters that would go into it, which are the part of the X. And we don't know how well the engine's going to work. And so we're going to simulate using a high fidelity simulator, a computer tool that when you hit go, it operates like an engine, and we can measure performance variables like that real engine. And if we do that, then maybe we can then pick the best parameters. But that computer tool, even though it's cheaper than building the real engine, it still takes a long amount of time to run for every single iteration, or it's just costly to get our hands on. And so so that's kind of one example of this F, where the F, so this sort of fits within the realm of what we call simulation optimization. Where instead of building a function, you build a model of the process that you want to design. So that's one example of what this F could be. F could be, more simply, a mathematical expression with no fixed form. There could be, the thing you're trying to optimize, just one second, the thing you're trying to optimize could be the integral of something else, but it may actually be impossible to take that integral. So I could say, as an example, integral of something else that we don't know the integral for. So we might be able to approximate the integral numerically in a computer, but we're not actually able to calculate the closed form expression for the integral. So it's really costly for us to do this numerical approximation every time we want to try to take this integral. There's a question? So in the question was, what does minimization mean in the previous example? So the idea would be, let's say I want to maximize the thrust generated by a jet engine. So maximization there would be minimizing the negative. So I might say the output of the simulation is a thrust number. And those thrust numbers, if I just turn them into negatives, then they fit within this minimization framework, or I could just call it maximization, it's fine. But that would be kind of an example. I want to choose the parameters that maximize thrust. Does that answer your question? Yeah.
What is the range of that expression? For example, thrust engine. How do you define the conditions for a particular say, engine?
Well, so you say the range of it. Well, I mean, so that is going to go down to the people who are building the engine. They're going to say that we can accept fuel oxygen mixtures from here to here, from this range to this range, for example. And that would define this subset X that I'm calling up here. So this could be the Cartesian product of all of those different conditions. So you could say, I need my fuel air mixtures to be, I can only accept ones between 40% and 60%. So then in that dimension, it'll go from 40 to 60. Then you can say, and I do have an adjustable size for this particular part. Well, that size range goes from here to here. Well, that will be the other thing. So all of those things will be crossed together and we'll end up forming this subset here, which will just kind of capture all of those. Does that answer your question? Yeah, sorry, for those lines, the question was, how do I form the ranges for these things? And these examples I'm giving you are not examples that we're going to specifically be working on. I'm just trying to give you a motivation of the range of problems that you can handle with this kind of engineering design optimization framework. Thank you. So there's a question on Zoom. So, so the parameters that go into the function are real world attributes that somehow affect what we're trying to optimize. And so, yeah, that's the idea here, is that you have a system, a real world system, and I didn't turn on the camera here. Let me do that. So you have a real world system that that you have some control over certain parameters, and that control, sorry, let me just spotlight this. And pan over, apologies for this. There we go. Are those online? You should be able to see in the class. Apologies for that earlier. All right, so yeah, the idea here is you have some system and it has a bunch of degrees of freedom that are left over that you as an engineer or your stakeholders, the people you're working with on your team, they don't know how to set those things. They don't know what the right fuel air mixture is for this jet engine. It could be anything. They don't know what the right one is. They know there's a bunch of ones that the engine won't blow up in. So maybe the mechanical engineers know that as long as we keep it above 40 and below 60, the engine won't blow up, but they don't know which one produces the maximum thrust. So they need to do an experiment, and they've formed a simulation that simulates the jet engine. So you can put in these different things and see how much thrust you get out of that. And then that thrust will be the thing you want to maximize. And so we're trying to figure out what the best one is, using a computer tool to help us figure out that maximum. All right. Let me see if there's any follow-ups there. Okay. All right. So then, other sorts of examples. F actually could be the physical system. So it could be the jet engine. As an example of this, there's a guy I know, his name's Lee Cronin. He works at the University of Glasgow. And he is a chemist. And he is interested in a number of sort of inorganic chemistry, primarily, but he's interested in how do you find novel combinations, novel compounds, chemical compounds that have interesting properties. And so part of what he does in the discovery process is they started out basically by taking a 3D printer and they kind of gutted it and turned it into an automated chemical reactor. And so in that case, you can actually have it has a bunch of constituent compounds that it can grab, like a little robotic arm, and it can combine them in a little reactor that's underneath a camera, and they can then generate these reactions, study the reactions, and then flush the reactions out and start a new reaction. And so he was able to create an automated system where he could ask for certain properties. So from a fundamental science point of view, you could say, are there certain types of droplets that when you put into a beaker together, when they interact, they kind of chase each other around like a swarm or something like that. Well, in that case, he could put that in as like the thing that he could come up with an index of swarminess and say, I want to maximize this index and find the right compounds that when I drop into this creates droplets that create the sort of most swarmy-like patterns. The other things he does is actually in pharmaceuticals, he does automated discovery of drugs that have particularly useful pharmaceutical properties. And so that's another thing that he can automate through this process. So in this case, you have a computer that's deciding which compounds to combine, doing the experiment, looking at the outcome, and then from that outcome, deciding what to do in the next experiment in a totally automated loop. And so that's an example where the optimization objective is not mathematical, it's not even computational, it actually is the physical system. Or the jet engine. You could imagine if you gave the computer the control of the jet engine, it could try a bunch of different parameters on its own, changing the fuel oil mixture, looking at the thrust, resetting the problem, and so on and so forth. Likewise, there's a group, Georgia Tech, that has a, let me try to get rid of this bubble here if I can. And now, there we go. So that has this thing called the Robotarium. And so this is an NSF-funded project where they have a bunch of swarm robots about the size of your hand that are in an arena about the size of maybe half this room, maybe a little bit less than that, a third of this room, that has walls up. They have chargers all around the outside. And if you say, I would like to try a swarm robotics project, but I don't have access to 100 robots, but I can write the software for it, you can actually send your software to Georgia Tech and for free, and they will then, in an automated way, download the software onto the robots, run the experiment, send you the video data and all the telemetry and all that stuff back to you. The robots automatically reset, recharge, and then they wait for the next job that's been queued into them. And you can imagine wrapping around, let's say you had a parameter that you wanted to optimize on these things. Maybe it's at what battery percentage does each robot decide to go and recharge itself or something like, because you don't want a robot that kind of get stuck out there. Well, you may not know the right battery percentage for each job. So you could imagine optimizing that in an automated way, because an automated system can naturally deploy an experiment, gather results, reset the experiment, and do it all on its own. So in that case, you really can have a physical system being a tool that one of these methods from engineering design optimization can work with. Other examples could be a neural network. So in a neural network, here X are the weights of the network. So you say that I have a video that I'm looking at, and that video I'm going to run into a convolutional neural network or whatever, and we'll even talk about what all those things mean. But the basic idea here is you've got a bunch of different inputs. You could potentially have every different pixel in that video is an input that is could be combined in different ways to then try to find things like objects in that video. And so the weights of a neural network are sort of, the weights of how much do I pay attention to each one of these input features. And those weights, you don't know ahead of time. And so we have tools like stochastic gradient descent and so on that helps, it helps shape these weights automatically, but there's other ways you could do that as well. And so the neural network itself and its output performance, its loss function, you can think about this problem here as minimizing a loss function, where X are the weights of your neural network, F is the loss function, and then these are constraints on those weights. Whatever those constraints are, they might be totally unconstrained. It might be that every weight just goes from 0 to 1 and that's it. So this could just as well be a neural network problem as it could be one of these other problems. And then we'll give kind of other examples down the line, but this gives you a flavor of all of the things that I claim fit within this framework. So it's pretty broad reaching. And so our goal is to build an algorithm and of course, all of these notes are going to be available after class and posted online, that intelligently searches this space. So I'll say this domain to find solutions, which I'll call X, I guess I'll call them X hat, X vector hat, that are likely near optimal. And so that likely near optimal, this is what links us into what we were talking last time, where this is where that word heuristic comes into play. So we're basically not guaranteeing that we're going to find the best solution to these problems, but we're going to find a darn good one. And so we need to design an algorithm that helps us find pretty good solutions. So that helps us find these heuristics. And that algorithm is going to be our so-called meta-heuristic. And so we're going to be talking about the different types of meta-heuristics to solve this problem. Yes?
Why is it not optimal? Like, what stops it from being optimal?
Well, it could be the optimal, but we have no guarantee that it's going to be the optimal. So well, because there's no, in some of these, there's no mathematical expression that we can use as a proof certificate that this is the optimal. So if you're working with a physical system, you might say, wow, we found parameters that got thrust higher than we've ever seen thrust before. Maybe these are the best parameters for thrust for this jet engine ever. But then, you just give yourself a little bit more time and then somebody happens to find that, another set of parameters that then exceeds that. So there could always end up being, in order to quantify the for all X, this is the best X star, we can't really do that without a mathematical expression that we can lean on. So these are also, I'm going to say, we're leaning on, that's a term that I'll use in a bit here, model-free approaches. And what model-free ends up being is it basically means you don't need to know a lot about the system, but the downside of not knowing a lot about the system is we're never actually going to be able to guarantee that we have the best solution for this particular problem. All we can say is based on the experimentation, this is a pretty darn good solution. And you might actually be able to start this process with a good human guess as to what the solution will be. And hopefully the system will then optimize on top of that. So that's kind of our goal with why we have these meta-heuristics, is we're looking for a way for these computational tools to help us with this admittedly very hard problem. All right, so any questions about that motivation? Yeah. I would say that that x bar, or x, we'll call this x vector there. So this is sort of a possible solution, could be terrible. And I would say that I would use the notation star to say it's the optimal. And I'm going to say that that little hat that I put over there is going to be approximately optimal, or good, I guess I'll say, not best, but good. So if optimal is best, then the hat is good. And this isn't a notation I'll necessarily use a lot, to just kind of trying to formalize things to provide a little bit more of a structured context of where we're going with this. As we'll see, the types of problems that you handle with these nature-inspired meta-heuristics are varied. So the structures that are most convenient for us to use to describe them will also be varied. I won't always necessarily write this as a minimization problem, but I'm just sort of saying that all of the problems that we can handle, in theory, you could write them in this format. And so this is a very generic way to talk about the engineering design optimization problem, or the EDO problem. Okay, any questions online? Question online. So, so there's a question or clarification online. So model free means we have no mathematical equation to prove we hit the global optimum in the solution space. Model free means that's one of the things that model free means. Sometimes when you have a model, and I'll talk about this in a second when I talk about different optimization methods, just because you have a model doesn't necessarily mean you know that you're at the best. But typically, if you do have some part of a model, you can use that model to guide the search. Generally, these meta-heuristics assume that you have no a priori information, except for maybe an intelligent guess on an initial condition that helps you guide the search. And so we'll see a little bit of that more. So, so there are optimization algorithms that I'm just want to talk about, where you have to provide a mathematical model of the optimization objective, or of aspects of the optimization objective. But in most of the meta-heuristics that we talk about, then we, and I'll get to this in a second, then we actually assume we don't have that information ahead of time. So then a question, do I give an example of model free and model based? Let me move to the next section on optimization algorithms. I think the first optimization algorithm we talk about will kind of give a good example of what I mean by model free and model based. So the types of optimization algorithms. There's basically the categories that are kind of interest to us. So kind of surrounding this model idea, can somebody tell me, if you think back to even like high school calculus, if you were to optimize something, what would be some sort of mathematical tool that would be very helpful in guiding the optimization process for you to optimize things manually? What was that? Derivative. So I heard derivative online as well. The gradient. So it would certainly be nice if we had a gradient. So there are plenty of gradient-based optimization algorithms that are based on things like, you know, Newton's method, or, and I'll put in parentheses, stochastic, but gradient descent. And so these are examples where you are provided, you may not be provided F, but you are provided all of the derivatives of F. And so you might not know actually what F is, but somebody's told you that, but even though I can't tell you exactly what F is, here is a mathematical expression that explains how F varies with the first element of X, with X1. So, you know, like basically gives you all of the information about partial F X1, partial F X2, and so on, all the way up to partial F X in. And so if I have this gradient information, then that basically tells me the slope of the hill that I'm climbing or trying to find the bottom of. And that is extremely helpful in guiding my search. And so this is an example of what I mean by something that would not be model free, because I would have to provide some model of the optimization objective. It might not be the optimization objective, but it might be all the gradients for the optimization objective. And so there are a bunch of gradient-based methods that use gradient information to guide the search. So this is kind of like, you know, so this is sort of usually our first guess as to how we would like to approach optimization. But it turns out that in really ugly functions, you often can't really start with gradient-based methods because you get stuck. So if your f function has a bunch of local optima, for example, then each one of these peaks and troughs is where the gradient information goes to 0. And so you have a bunch of these local suboptima. And if you have no way to be able to somehow jump from one of these areas to another, you might not be able to get out of these traps. So these local suboptima, sometimes called traps, can be really difficult for gradient-based methods. And that's the reason, partially the reason why in neural networks, they have this kind of stochastic gradient descent. That's a heuristic that they've added on top of gradient descent, where they've made it a little noisy so that even though the gradient descent is trying to find the bottom of the tiny little bowl that it's in, the stochasticity allows it to hop into other bowls so that it hopefully can find the deepest bowl and then find the bottom of that deep bowl. And so that's really where gradient-based methods are strongest, is when you're pretty confident that you are in the neighborhood of the right solution. So I would call gradient methods, pure gradient methods, as sort of finishers. So you can imagine starting with a meta-heuristic that, and that will get you close globally. And then you can imagine then tuning with gradient methods. And there are ways in which you can adapt gradient-based methods to kind of do that. So those of you who have a little bit of background, again, in neural networks or whatever, or AI in general, you've probably heard of different learning methods that have a so-called step size. And you might start with a large step size, and then gradually over time, it gets to become a smaller step size. That is effectively this idea that initially you want to search over a very large space of solutions, and then over time, hopefully you're in the neighborhood of a good solution, and then you refine your search and just search that local neighborhood to try to find the best one. And that's the gradient really is for finding that kind of best solution. So we aren't, although you could add gradient information to any of the methods that we're going to talk about, we're not really going to focus on gradient methods directly. We use a different set of methods that I'm referring to as direct search methods. So gradient methods use gradient information as a kind of model of where we are right now. Do I know that I'm standing uphill? If I know that I'm standing uphill, then I kind of can infer that if I want to maximize, I should go in that direction. If I want to minimize, I can go in that direction. And I can use information at this point to tell me whether I need to go up or down. Direct search methods are optimization methods that have no gradient information. And so they have to figure out what direction they're going in by searching the space in a little bit more of an intelligent way and kind of maybe keeping track of where they're going. So some of you may have heard of things like extremum seeking control. This is not something that I'm going to talk a lot about, but I'm just mentioning it here. For those of you who have a background in extremum seeking, this is like an example of that. So in extremum seeking, this is often used in control systems. You can perturb that variable that you're trying to optimize in, say, a sinusoidal way. And then you can look at the output that you're trying to maximize or minimize. And based on the relative phase of the input changes and the output changes, you can figure out if you need to go up or down. And so the basic idea is if I'm not sure if that's uphill or that's uphill, if I walk back and forth in a sinusoidal way right here, and then I sort of watch how my height changes, then if my height is changing kind of in the same direction, so if I walk to, if I'm calling this the positive axis, if I walk in the positive axis and my height goes up in the positive axis, then that must be uphill. But if I walk in the positive axis and my height goes down, that must be downhill. And so an extremum seeking control, which is often used in physical systems, by looking at the relative phase of the sine wave you put in and the sine wave you put out, you can actually get gradient information out, and that'll help guide your search as to whether you want to go up or down. So that's kind of one example of how you can get something like gradient information, even though it wasn't provided to you. So a less control-based or physically based one that is commonly used, so an old algorithm for direct search, so I'll call this DS, direct search, is so-called tabu search, which is often abbreviated TS. So has anybody heard of tabu search or seen? No, okay, all right. So so sometimes if you go into design tools, then you'll see tabu search as an option so if you work at a simulation tool or something like that, if you want to do simulation optimization, you might be given the option to use tabu search. So it's kind of a classic tool. So the way tabu search works, it's a so-called a local search method. And so again, none of this is nature inspired yet. This is just giving you the background of kind of what came before. And so I'll call this, I might also call this a neighborhood search. And so what tabu search does is it's a single, you can think of it as a single agent or a numerical algorithm that has a state that stands in a particular position in the domain. So this is a particular X. And from there, it takes steps, small incremental steps away from that X. So from this X, it can move, it can move in one dimension or another, it can move in another dimension, it can move in some linear combination of those, but it moves in small steps. And as it moves in small steps, so I guess I can say it's from the current X, move in a small step and reevaluate F at that position. And if it's in, and then hopefully it moves to a better position than it is now. Where the tabu comes into place, so this tabu is it keeps track of old locations. It's supposed to be location. And avoids them in future steps. So super simple algorithm. If you have no prior information in your memory, you just choose randomly around you, step in any one of the directions you can step, the tiny little delta, tiny little step size. And then if you happen to have, so if I step to the right, I know that the position to the left of me, I've already done that. So when I'm in the position to my right, when I'm exploring the space around me, I avoid the step to the left because I've already been there. And so this is, in a way, not much better than a brute force search. You just sort of start it somewhere and it just tries to prevent itself from doing things it's already done before. And so that's, you can think of as a local search method because it doesn't make large jumps. It is a trajectory-based method where it starts in one position and it moves a little bit farther away, a little bit farther away. And so if it needs to get somewhere very far, it's not going to get there immediately. It's going to have to drift its way over there. And so we call that a local search method or a neighborhood search method with memory. And so I guess that's the kind of important thing here is that this one has memory. Other algorithms will not have memory. Yeah.
So what if, like, let's say you take a step in one direction, you realize you're going down, let's say try to maximize. So you want to go back the other way, but you can't step backwards. So what?
Well, so taboo search does provide ways. It doesn't get stuck. And so if you have a fully admissible, if there's a bunch of spaces you haven't stepped in before, it will tend to step in those rather than spaces it has stepped in before. So it does have ways to kind of tunnel out. So if you get to the end of your admissible, your feasible region, then of course it can move back. And I'm kind of glossing over some of the details of all of how taboo search, but the salient features of taboo search is from wherever you are, if you've got a bunch of spaces around you that you haven't stepped in, step randomly. If there's a bunch of spaces around you haven't stepped in, and a few that you have, avoid the ones you have. That's basically how taboo search works. Question in the back?
I understand that using memory, but how is this different from extremum seeking control? As in, even in extremum, we're taking a step calculation through and finding if that's good or bad. Here, obviously, you're doing the same thing. You're taking a step in one direction and finding if that's good or bad.
Right. Well, I would say that so you're right. All of these methods that are these direct search methods are likely going to do some sort of exploration to kind of build sort of an internal model of what's going on. The distinction between something like extremum seeking and taboo search is that in extremum seeking control, it's usually an application specific thing. So taboo search is often implemented on a computer, often in a discrete optimization setting, whereas extremum seeking control is often even implemented in a physical system, even not while you're optimizing, but while you're actually operating the vehicle. And so a lot of times the notion of them is roughly the same. Like in extremum seeking control, there is no memory to sort of keep track of like things that I've done in the past, because extremum seeking control is really about tracking the optimum. So it's like if I build, it might be that as I'm driving a car, based on the amount of wind I'm getting, there might be an optimal throttle that I need to put on the car in order to sort of somehow compensate for this wind. And so to find exactly that throttle level for this wind, I might need to use extremum seeking control to do that. Now, if the wind changes, extremum seeking control will then go and try to find the new throttle level. And so it's not looking for like an answer to a problem, it's trying to track an optimum that changes over time. Whereas taboo search, you're saying, I've got a really complicated problem. It's it's a shortest path problem or something like that. Go find the shortest path for me, or go find the best choice for this one static variable. And it's going to try, well, I'm going to try this, I'm going to try that, I'm going to try that, and eventually it'll find the best choice. So there's kind of a difference in the applications and how they use. Does that answer your question? Okay. Let me make sure there's nothing online. Again, I'm just trying to cover some of the history of these. So they say it's a random walk for the steps for taboo search. And yeah, I think, again, there are variations on taboo search, but for the purposes of this class, you can consider taboo search as basically a random walk around the objective, around the feasible space with memory to prevent backtracking. So that's basically all taboo search is. So I just want to kind of, basically I'm trying to define what it means to be taboo, and to this idea that we're trying to come up with intelligent mechanisms to search through this space. Again, not nature inspired or anything like that, but just one of these benchmarks that a lot of people will use. In simulation optimization, taboo search comes up a lot, and so on. So, that's kind of an example of different non-nature inspired direct search methods or trajectory-based methods. But we really, and so then we also can have, under direct search methods, nature inspired methods. So direct search, we're going to then now investigate nature inspired methods in this class, and those include things like the genetic algorithm, so-called, as we'll hear talk about later in the class, things like ant colony optimization, things like particle swarm optimization, and maybe a few others. And you could argue that even something like the simulated annealing So these are all methods for intelligently searching these spaces, not using kind of like taboo search just kind of makes sense, right? It's just a random walk with memory to prevent backtracking. So these nature-inspired methods say, well, you know, if you think about it, there are certain processes in nature that appear to also be intelligently searching spaces. What can we learn from them that we can maybe use to guide our search in maybe a way that's a little more clever than just a random walk with, you know, to prevent with backtracking prevented. So that's kind of what we're talking about here. So again, so we're focusing on direct search methods, and in this class, we're sort of exploring nature-inspired methods. Now, our first kind of focus is going to be on moving towards the GA and other evolutionary algorithms. That's where we're starting off. All right, so if of the different types of methods, there are basically two categories. So if I go through here, I can say that like GA, these three, which we will talk about in this class, fit into one category, and simulated annealing fit into another. And those two categories are population-based methods which, as we will learn, are things like the GA, ACO, PSO, and many more. And let me just make sure I didn't have any other notes that I wanted to put in there. And you could also include, well, okay, well that's, yeah. And then there are, and then these are basically, and we'll see this, but most of these fit into the category of evolutionary algorithms, most of the optimization versions. So algs often fit into this area. And so we'll define what evolutionary algorithms are momentarily. And then the other category, which is sort of like the old school taboo search, are trajectory methods. And those are like taboo search, simulated annealing, which again, we'll talk about in a later lecture, what simulated annealing is and so on. And so we've seen that in trajectory-based methods, you're basically starting in a place, a guess for what the best solution is, and then walking around in a trajectory, hopefully leading to better and better solutions along the way that you're walking. So it's a single agent, if you like, or it's a single guess, and then that guess is perturbed to hopefully find better and better guesses. So we tried this fuel air mixture, we're gonna go to a slightly better fuel air mixture, maybe a slightly worse, but then not go to that worse one again, and so on and so forth. And so there are these trajectory methods, which are kind of the old school way of thinking, and then there are these population-based methods, which are what we're now talking about. And that the large set of population-based methods, at least where they started, were these so-called evolutionary algorithms, which is where we start in this class. As we get into population-based methods like ACO, we'll find out that ant colony optimization can actually be viewed as very closely related to these evolutionary methods, even though it itself is not formally based on evolution. Particle swarm optimization, which we'll see, doesn't actually have the same feel as these evolutionary algorithms, but it does borrow this population characteristic. And so not all population-based methods are evolutionary algorithms, but I'd say that this ball got rolling down the population-based method way with the evolutionary algorithm. So that's why we're going to kind of start with evolutionary algorithms. Okay, so in order to get there, so what do I mean by what do I mean by an evolutionary algorithm, and how does it relate to direct search? Well, if I want to sort of outline what is a basic flow chart for a direct search look like. And I think some of you could probably guess what this might look like. You basically make an initial guess, you evaluate that guess, you run an algorithm to figure out your next guess, figure out if you can stop, and then kind of restart. So the basic flow chart is I've got an initial guess, and then that thing goes into my simulation model, or a function. So this basically goes into my F, or my sim model, or my real system. I guess I could have written those all in different colors here, but maybe I'll put a little bar in between them. So we take our initial guess, it goes into the function that we're trying to optimize. That's going to give us an answer, an output metric, which will take us into the actual optimization algorithm. So we get an output metric. And then that is going to go into our optimization algorithm, which just basically figures out what is the next guess. And then from there, you know, these algorithms eventually have to stop. And so we go into a decision here where we ask, is it time for us to stop this process? And if so, then we give the previous guess as our results. Otherwise, we take our new guess and we run it back into the function and restart this process. And what goes into the termination condition? This could be a computational budget. Or it could be convergence conditions. In other words, it's taken a lot of budget to calculate this function over and over again. We might say you can only run that jet engine 10 times. So after you run it 10 times, we have to end. So it's the best you got in that 10 times. Or it might be that we've provided you enough budget to run this until you can't get any better. So like the convergence conditions here, these could be on either your guesses X, or more often on the optimization criteria F of X. And so the idea is, have these changed very much? So if your optimization algorithm keeps telling you to beat around a neighborhood of a single X, then your termination conditions might say, we're not moving very far, let's just stop here. Or the optimization criteria might be based on convergence of the optimization objective. And so if you found a particular maximum and you're not really getting any better than that, or when you get better than that, it's just marginally better, and you define what it means to be marginally better. So you might say that the last 100 iterations, you didn't improve more than this margin. So based on that, we're going to stop this right here because we don't think you're going to get any better. And so those are so these conditions are often up to you. They're very subjective, but there's going to be some sort of termination condition. So when we talk about these algorithms, we're often not going to talk in detail about this because it really is up to you. But I hope you sort of get that there's different ways you can decide when to stop this loop. But this search loop, again, because these are meta-heuristics, finding heuristics, we cannot ever know that we actually got there. So these could go on forever. And so that's why we have to have this termination condition. So this is a basic direct search algorithm. So now I'm saying, well, then what makes it where does the evolutionary algorithm come into play? Was there a question?
The model also refines with each iteration. The model refines with each iteration.
So the question was, is the model refined with each iteration? And in this, I'm basically considering static optimization problems. So there is one jet engine, and so it's not like we're changing the model, but we are plugging in our parameters. So it might be that our parameters are a 100-dimensional vector. And so you can think of the 100-dimensional vector as really changing the jet engine every time, but the way in which those parameters plug into that engine isn't going to change. So there's one jet engine. There's just might be a gazillion ways to configure that jet engine, and we're just walking through those. So the model isn't changing, but the ways we configure the model are changing every iteration. Does that make sense? Okay. Let me make sure there's no clarification questions online here. Okay, good. All right, so this is a basic direct search. It fits taboo search. It fits pretty much all of them. You could drop in whatever your optimization algorithm is, and it basically just changes there. The rest of this stays the same. So what makes an evolutionary algorithm? So the modification for this is that we actually send multiple guesses around the loop simultaneously. So we use a population of possible guesses, of possible solutions, at each iteration, and then reshape the population based on their relative success. So a population of possible solutions at each iteration, and then reshape population based on relative success. So the idea here is saying, rather than putting in one guess as to our optimizer to the evolutionary design optimization problem, let's put in 10. And let's just evaluate all 10 simultaneously. So then we get 10 outputs. So we go from 10 inputs here, and we'll get 10 outputs here. And then when we go into the optimization algorithm, we're going to say, for these 10 individuals that we put into this model, they each, one of them had these 10 different outputs. And so based on those, then we can see maybe that there's a couple of those 10, maybe 3 out of those 10 all look pretty good. They're all close together. We could sort them all, and maybe one would clearly be better or whatever, but we're just not sure randomly. And we might have ended up found that of those 10, these are very far apart. So those 10 solutions might be very far apart in X space, but they're very close together in F space, those top 3. So we might get rid of the bottom 7 and keep those top 3. And then the bottom 7, those might be drawn totally randomly. And so we basically reshaped the population based on how well they did relative to each other. So when we only had a single solution in a trajectory method, we only really had the history of that single solution to compare to. Now we can run multiple solutions in parallel, and they can not only respond to their own history potentially, but then they can compare to each other. And then that can tell us when to actually give up on some searches. So yeah, you could optimize locally in this area, but we found another solution that over the last 5 iterations has always been better than the solution that's over here. We should just abandon this area and put more computational effort into searching that area. So take the 4 solutions that are in this area and put them over there, and now we'll have them search in parallel over there. So this process is going on in parallel. And so it's evaluate in parallel and compare outputs. Now this can be very computationally costly. We still need to run that jet engine 10 times. We're just doing it 10 times all at once rather than one time evaluate, another time evaluate, and so on. So now there are some systems where this is very, like you might have a natural parallelization in your system. You might very easily be able to run, it might be that your function is relatively cheap to compute and you have 10 cores on your computer. Well, you may as well evaluate all 10 individuals simultaneously on the different cores of the computer, and each core could evaluate F. Because evaluating F, maybe that is something that you would only do on one core in the trajectory-based methods anyway. So the other 9 are just sitting there idle. So you may as well just go ahead and evaluate all 10 of them in parallel, because those resources are going to sit there idle anyway. So this can be very good for making use of distributed and parallel resources as well. So that's what makes an evolutionary algorithm, the use of a population. It's nothing about genes or anything yet. We haven't gotten there. An evolutionary algorithm is all about a population that gets reshaped over time. Okay. So any questions about that? Yeah.
Like take random 7 other instances or guesses. So instead, like, is there a way where you can explore the 3 that were good and like we choose some guesses that are close to it or something? So
right.
That you don't, again, randomly they might perform worse.
Right. So I think the question was, you're asking about this process of, if we have 3 that are much better than the other 7, then is there a way of, are you saying, of keeping the 3 and throwing up? Right.
Can that be closer to the 3 that are?
Yes. So there's a question. So can the next, if we have one of that hypothetical example where I have a population size of 10, 3 that have done pretty well, 7 that have done really poorly, then in order to choose the next 7 to replace them, can they be based on the other 3? And yes, they often are. So that's kind of what I mean by, instead of using those 7 to explore this dead end here, I'm going to reallocate them to be closer to those 3. And so it's kind of like having multiple step sizes. So rather than having a trajectory-based method that has a tiny step size where it can only search here, now that I've got those other 7, I can have each individual of the 3 existing use a small step size, and I can redeploy those 7 almost like they're a giant step size. So they can now be closer to them, but far enough away that they'll stay out of the way of the other ones. So it allows me to kind of do a coarser grained search of a region. It's sort of an in-between a fine grained search and a coarse grained search. So that's something that I can do with population-based methods. All right. Any other questions about this basic idea? Questions online? What do I mean by, okay, so it looks like that was answered. All right, so in the last 5 minutes here, then let's sort of set up kind of the, oh, so yeah, so there, does an evolutionary algorithm have memory? In general, I mean, really an evolutionary algorithm, again, it's just a general definition for an optimization algorithm that makes use of a population where the population ends up, the performance across the population is what determines what individuals survive and what individuals perish. That's the generic definition of an evolutionary algorithm. Now, each individual may actually itself, in your algorithm, you could build an evolutionary algorithm that does have memory from each sort of individual, but that isn't a necessity. So typically the evolutionary algorithms that we're going to talk about initially here, there's no memory at the kind of individual level, but there is memory in a population. So you can kind of think about the demographics of the population as a sort of memory. They stuck around for this long, so that kind of means something, but we don't necessarily have a memory of every place that each individual's been as it's been moving around. Yeah.
So the reason that's evolutionary is because kind of like the best solutions get like they have more, I guess, children, they have more like people, like more solutions around them, while the ones that were worse off end up dying if you just cut them off.
Right. So So, and we're going to talk about this here in just a bit, or on Tuesday if worse comes to worse. But the word evolution biologically just means the change in the frequency distribution of alleles in a population. We'll define what we mean by an allele. So it's this idea that there are strategies that are getting more numerous and less numerous in a population. That is what evolution is the idea that there are persistent strategies that outperform other strategies stay in a population, and strategies that consistently underperform other strategies are moved out of a population. That's what an evolutionary algorithm is. So we're competing among strategies directly, as opposed to waiting for an individual to kind of run into a strategy and compare to its history, as trajectory methods would do. All right, so any other questions? So it's very different than the memory that tabu search does, where tabu search is keeping track of where it's been and avoiding that location. A pure genetic algorithm or an evolutionary algorithm will sometimes revisit the exact same spot. And we can be clever in how we design our algorithms to make that less costly to do, but there's nothing fundamental about how the algorithm chooses the next space that will avoid that, going to that old spot. Okay, so the only kind of important note that I want to add, there was a question earlier about constraints. I've kind of not really talked much about how to deal with constraints. And I'm not going to talk too much about this because this is kind of a sort of a tuning detail on the side here, but I do want to say that it is important. So there is, when you're randomly choosing solutions, so randomly chosen solutions may fall outside of your feasible set. And remember, I call that feasible set, scripty cal X here. And so what do you do with that? So there are a bunch of options you can do. You could discard and redraw. And eventually you'll get one that's inside your feasible set. Sometimes you actually leave those solutions in if F can be evaluated there. Now, why would you do that? It may be that in your simulated model of the jet engine, that the parameter that your algorithm wants to try is outside the parameters that the mechanical engineers told you could use. But your simulation model can still simulate them. They're just outside of safety parameters. Well, if you evaluate them there, you may learn something about the thrust characteristics of that engine that can only be learned by pushing the engine beyond its limits. And that can give you things like gradient information. So even though it might be unsafe to do that experiment in real life, if it's still safe to do it in a simulation, just let it do it. And then you might end up learning that even though that's not a feasible solution, I can't return that solution, leaving that solution in the population might actually help guide my search for better solutions rather than just choosing some arbitrary one that was in the feasible set. So what we often do is we simply penalize infeasible solutions, but still allow them. And so you might take their f of x and you might actually add a penalty to it because it's outside of the feasible set. But if you've got a huge performance improvement by going outside of your feasible set, that tells you that maybe being on the edge of your feasible set is a really good place to be. And that will help guide future solutions to be closer to the edge. So that's the reason why you don't just necessarily discard things that are outside of your feasible set.
Is this akin to regularization?
Online. And there's a question, is this akin to regularization? So those of you who have some neural network background know that when you minimize a loss function for a neural network, you often add in penalties for so-called regularization. And I would say that it's related to by penalizing your weights in that way. But in a neural network, you're often not worried about your weights being too large or too small. but there's other things that the regularization is doing. But it is the same sort of approach here, is to penalize rather than formally constrain, and that helps kind of guide the optimization. So it's related, but I don't want to say it's equivalent.
Also, in process control, there's soft constraint enforcement, and I believe they follow a similar logic.
Right, and so yes, the idea of soft constraints is kind of a question that came up online, is very much related to this. So in process control and other versions of control, we often do penalize constraint boundaries as opposed to making hard constraints. We call those soft constraints, and it has kind of a similar feel. But anyways, I don't want to keep you any longer than that. That's we'll start off on the actual sort of genetics of the genetic algorithm next time. And thanks for your patience.
Thank you, sir.
Thank you.
Thank you. All right, so online, I'm about to end the meeting unless there's any other quick questions. If not, have a good weekend, and I will see you next week.